At Jupiter's North Pole, there are 8 massive cyclones, each one bigger than the state of Texas, arranged in a perfect ring around a 9th cyclone sitting dead center, like the numbers on a clock. They have been spinning there in that exact geometric formation for over a decade, without merging, without drifting apart, without breaking the pattern even once. By every rule we understand from studying storms here on Earth, that arrangement should not be able to exist. And when NASA scientists first saw it clearly, they didn't have an explanation ready. They just had the pictures and a question nobody had ever needed to ask before. This is the story of what NASA's Juno spacecraft actually found when it became the first mission in history to look directly down at Jupiter's poles, and why the storms it discovered there are still, years later, breaking the physics we thought applied to every rotating planet in the solar system. To understand why this discovery mattered so much, you first need to understand what nobody had ever managed to see before Juno arrived. For centuries, everything we knew about Jupiter came from a strictly side-on view. Every telescope on Earth, every previous spacecraft, including the historic Pioneer and Voyager flybys of the 1970s, and Galileo's long orbital mission through the 1990s and 2000s, observed Jupiter from angles that kept its poles essentially hidden, tilted away or foreshortened into blurry, unusable smears at the very edge of every image ever captured. We had a detailed picture of Jupiter's equator, its colorful cloud bands, and its famous Great Red Spot, the largest storm in the solar system, big enough to swallow Earth whole. But the top and bottom of the planet, the poles themselves, remained a genuine blank spot on the map of our own solar system's largest planet right up until 2016. That's when NASA's Juno spacecraft, after a 5-year journey from Earth, finally settled into a highly elongated polar orbit around Jupiter. A deliberate, carefully engineered choice that would let it do something no previous mission ever had: fly directly over the top and bottom of the planet on each pass, looking straight down rather than skimming past from the side. That orbital design wasn't a small technical detail. It meant Juno would swing in dramatically close to the cloud tops on each pass, then swing back out to a much greater distance, an orbit shaped less like a circle and more like a long, thin loop, chosen specifically to protect the spacecraft's electronics from Jupiter's punishing radiation belts, some of the most intense radiation fields anywhere in the solar system, while still giving its instruments a direct, unobstructed view of the polar regions nobody had ever properly photographed. Juno wasn't the first mission to orbit Jupiter, but it was the first to dip toward both its poles, and what its cameras revealed on that very first orbit reshaped scientists' understanding of the planet immediately. JunoCam, the spacecraft's visible light imager, captured the first ever clear close-up pictures of Jupiter's North Pole, and what came back wasn't the familiar banded striped Jupiter everyone recognized from decades of side-on photographs. It was something else entirely. A strange, bluish region, utterly unlike anything else on the planet's surface, dominated not by the horizontal bands of clouds circling the equator, but by a tight cluster of enormous, distinct cyclones, swirling storms with clearly defined edges, arranged in a pattern that looked, if anything, almost deliberate. A single massive cyclone sat directly at the pole, surrounded by 8 more, spaced with an almost eerie regularity, as though bowing in formation around the central storm. Turn the spacecraft's cameras toward the South Pole, and a similar, though not identical, cluster of storms appeared there too. 5 cyclones this time rather than 8, still ringed around a central polar storm, still holding a stable, ordered formation nobody had predicted. Nothing like it exists anywhere else that we know of in the solar system. Saturn, Jupiter's fellow gas giant, has a single massive hexagonal jet stream pattern at its north pole, itself strange and well studied for decades. But Jupiter's polar arrangement, a tightly packed ring of nearly equal, individually distinct cyclones, all persisting simultaneously without merging into one another, had never been observed on any planet before Juno's cameras finally caught it directly. And it remains, even now, unique among everything we've documented anywhere in our solar system. That persistence is what turned this from a striking photograph into a genuine scientific puzzle. Using both JunoCam and a second instrument called the Jovian Infrared Auroral Mapper, or JIRAM, which detects heat rising from deeper inside the atmosphere rather than relying on visible sunlight, scientists have now tracked this system of polar cyclones continuously since 2016, watching it through repeated close flybys, sometimes called perijovies, that bring the spacecraft skimming just a few thousand miles above Jupiter's cloud tops, roughly every couple of months. And what they found is that the storms aren't static. They drift slowly in a well-documented atmospheric process called beta drift, caused by the interaction between the Coriolis force and each individual cyclone's own rotating wind pattern. That same beta drift process happens with cyclones here on Earth too, part of the same basic physics that governs how hurricanes curve and migrate across our own oceans, nudged along by the way Earth's own rotation interacts with a spinning storm's internal wind field. But here's exactly where Jupiter breaks the pattern completely. On Earth, Cyclones experiencing beta drift never actually reach the poles. As they drift poleward, they run out of the warm, moist air that fuels their rotation. The cold, dry conditions near Earth's poles starve them of the energy they need to keep spinning, and they weaken and dissipate long before they'd ever get close enough to cluster the way Jupiter's storms do. It's a hard physical limit baked into how cyclones work on our own planet, one so consistent that meteorologists treat it almost as a given, a boundary condition built into every hurricane model ever developed for Earth's atmosphere. On Jupiter, that limit simply doesn't seem to apply in the same way. The cyclones drift toward the pole and then stay there, packed together in a stable, long-term formation that has held for the entire decade Juno has been watching. Without the storms merging into a single feature or drifting apart and scattering across the planet, the way basic beta drift physics would predict for a system like this if it behaved the way Earth's atmosphere does, scientists are still actively working out exactly why. Jupiter's atmosphere is vastly deeper and more energetic than Earth's, with no solid surface underneath to sap energy away from storm systems the way land and ocean interactions do here. And Juno's data has revealed that Jupiter's powerful jet streams, the fast-moving belts of wind that separate its cloud bands, actually extend much farther down into the planet's interior than researchers had previously modeled, adding a whole additional layer of atmospheric depth and energy that simply has no equivalent on our own planet. In fact, one of Juno's major findings, confirmed through careful gravity field measurements taken as the spacecraft passed close to the planet on each orbit, was that these jet streams penetrate roughly 3,000 kilometers beneath the visible cloud tops, far deeper than most pre-Juno models had assumed, meaning the entire engine driving Jupiter's weather is operating on a scale that dwarfs anything happening in Earth's comparatively thin, shallow atmosphere. Researchers studying the polar cyclones have developed new models specifically trying to account for how Jupiter's uniquely deep, uniquely energetic atmosphere might allow this kind of stable cyclone cluster to form and persist in a way that would be physically impossible in Earth's atmospheric envelope. But a fully settled, universally agreed explanation for exactly why the geometry holds together this precisely for this long still doesn't exist. It remains one of the active, ongoing mysteries Juno's mission was specifically designed to help solve, and one that continues generating new papers and competing models years after the storms were first photographed. And the poles weren't the only place Juno found something that broke the existing rulebook. As the mission continued year after year, extended repeatedly by NASA well beyond its original planned lifespan, first through 2021, then again through September of 2025, Juno's orbit was deliberately reshaped over time to bring it closer to several of Jupiter's largest moons. Encounters made possible specifically because mission planners confirmed the spacecraft's evolving flight path no longer posed any meaningful risk of accidentally contaminating Europa, one of Jupiter's icy moons considered a leading candidate for hosting a habitable subsurface ocean. That extended mission allowed close encounters with 3 of Jupiter's 4 largest Galilean moons, Ganymede, Europa, and Io. And one of those encounters at Io produced a discovery that stunned even the scientists who had been studying this system for years. Io, Jupiter's innermost large moon, has long been known as the most volcanically active body anywhere in our solar system, a world constantly reshaping its own surface through eruptions driven by the intense gravitational squeezing it endures as it's caught between Jupiter's enormous mass and the gravitational tug of neighboring moons, a process called tidal heating that essentially kneads Io's interior like dough, generating enough internal heat to keep the moon's surface in a near-constant state of volcanic upheaval. But in 2024, using its Jovian infrared auroral mapper instrument, developed and contributed by the Italian Space Agency, Juno detected something even by Io's own extreme standards. A volcanic hotspot in Io's southern hemisphere, larger in surface area than Earth's Lake Superior, releasing eruptions carrying roughly 6 times the combined total energy output of every power plant on the entire planet Earth combined. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the moment plainly. The mission had 2 especially close flybys of Io during its extended mission, and while each one had already exceeded expectations on its own, the data from this particular, more distant flyby genuinely stunned the team, representing the single most powerful volcanic event ever directly recorded on the most volcanically active world humanity has ever studied. Juno's continued observations have also given scientists their first ever look at Io's subsurface temperature profile, essentially a direct read on what's happening beneath the moon's visibly tortured surface, offering real insight into its internal structure and exactly how its relentless volcanic activity is actually being generated and sustained deep underground. Insight that simply wasn't available from surface imagery alone, however dramatic that imagery already was. Comparing images of Io captured across different flybys in 2024 also revealed visible physical changes to the moon's surface between passes, active proof, captured in real time, that Io's landscape is genuinely, continuously reshaping itself. Not simply the frozen relic of ancient volcanic activity, but an actively churning surface, changing on timescales short enough for a single spacecraft's repeated visits to actually document the difference. Meanwhile, back at Jupiter itself, Juno's other instruments have continued uncovering complexity nobody expected to find. In a planet many people assume we'd already fully mapped decades ago, the spacecraft's magnetometer data has revealed that Jupiter's magnetic field is nothing like Earth's comparatively simple, single-axis dipole field. Instead, it shows multiple embedded poles scattered across a genuinely complicated, tangled network of magnetic structure, one that turns out to be significantly more convoluted in Jupiter's northern hemisphere than in its southern hemisphere. And asymmetry researchers are still working to fully explain. Juno's radio science measurements have similarly shown that Jupiter's atmosphere carries real internal structure at depths scientists hadn't previously been able to probe directly, adding yet another layer of complexity to a planet that, before this mission, most people, including many scientists, assumed had already given up most of its major secrets. As of 2026, Juno remains actively operational, well past its original planned mission end date, continuing to send back new images and data from an orbit that has been deliberately allowed to slowly degrade over time. In May of 2026, during one of its recent close passes, Juno's Stellar Reference Unit, an instrument whose primary job is actually just navigational star tracking rather than science imaging, but whose extreme sensitivity in low light makes it a genuinely capable secondary science tool, captured a detailed image of Thebe, one of Jupiter's smaller inner moons, believed to play a direct role in feeding dust into the planet's faint outer Gossamer Ring system, an unplanned scientific bonus from a system originally built purely for spacecraft navigation. Eventually, Jupiter's own powerful gravity will pull Juno's slowly decaying orbit inward until the spacecraft is deliberately allowed to burn up in the planet's dense atmosphere. A planned, controlled end designed specifically to protect any chance of contaminating Jupiter's potentially habitable icy moons, particularly Europa, a place worth protecting from any stray earthly microbes that might have hitched a ride on the spacecraft nearly a decade ago. But until that final, deliberate plunge happens, Juno keeps watching, and it keeps finding things nobody expected. A ring of stable, individually distinct cyclones circling each pole in defiance of the basic atmospheric physics that would tear apart any equivalent formation on Earth. A moon undergoing the single most powerful volcanic eruption ever directly measured anywhere in the solar system. A magnetic field so tangled and irregular that it barely resembles the tidy, simple diagrams found in textbooks. Jupiter, it turns out, was never the simple, well-understood giant most of us grew up picturing. It took a spacecraft willing to fly somewhere no previous mission ever had, straight down over the poles rather than skimming past from the side, to reveal just how strange this planet actually is, right in our own solar system, hiding in plain sight the entire time.